Okay, hey folks, how's it going? Finishing up our week 13 content talking about photochemistry. So this stuff is really cool. So let's get into it. So the first thing that I want to review is just basic absorption. So you've talked about this at a lot of classes, particularly the Beer's law, the Beer-Lambert law, right? But I want to build up where that comes from. Okay, so there's two things that we could look at in terms of what happens, when we have a sample of absorbing molecules and they are exposed to some incident beam of radiation, right, which could be visible, ultraviolet, infrared, etc. And some of the intensity of that radiation is absorbed by the sample. So the light that comes out here is less some fraction that's been absorbed. Okay, so we could describe that as the optical depth, which is really like a measure of how how deep into the sample light will penetrate. And that's actually the natural log of IO over I. Okay, the incident beam over the transmitted beam. What you're probably more familiar with is something we call transmittance, which is the ratio of the transmitted beam over the incident beam, right? And which will be a number less than 1. So in the event that there's no absorbing sample, right, I over I naught is the same and transmittance is 1.0. And often we talk about it in terms of percent transmittance, right? We multiply that by 100 to make a percentage out of it. Okay. And then similarly, we could also now talk about our transmittance in terms of the optical depth. And so that becomes e to the negative tau. And that negative, right, will flip the sign. So it is what you're used to seeing, the transmitted beam divided by the incident beam. Okay. So instead of thinking of that in terms of transmittance, we could think of it as absorbance. And absorbance is the negative log, and historically that's a base 10 log, right? Okay. But the actual correct definition of that is to look at it in terms of base E. So actually, let me erase that really quick, and I'll talk about the base E, the natural log, in a moment. So what this means, so the natural log of 10 is the number 2.303. And we can convert an absorbance into an optical depth just with some simple algebra. If I say the factor 2.303 times absorbance, that just gives me the optical depth. So optical depth and absorbance are very closely related. It's really just a difference of the base 10 versus base E metric. Okay, so that number 2.303 is the natural log of 10. Okay, so now going forward with this, if we consider the base E measurement, if we break down tau, so here I've written tau, the optical depth, as the ratio of intensities, but actually we can talk about it in terms of things in the sample. Okay, so sigma, this is called the absorption cross section. Okay, and it has units of centimeters squared per molecule. So it does have cross-section units. Okay, there's this number N. That is the concentration of molecules in molecules per cubic centimeter. Okay, so really we call that a number density, right? So that's molecules per cubic centimeter. And then now L, that's the length, the path length of the sample cell, which is typically given in centimeters. So you can see now this is why we actually like the molecule per cubic centimeter unit, right? Because when I multiply all these through, a square centimeter divided by a molecule times a molecule per cubic centimeter, times a centimeter cancels out all of those units. And optical depth is unitless, okay? So that's the base E measurement, all right? Which I would actually say is more physically correct, okay? So there is a, let me see if I can draw it with a different color that stands out. Right, there is an exponential decay of light intensity as it goes through the sample. So as light is passing through that sample, it exponentially decays with path length. So the base E is actually more of the correct version. That base E gives us that natural log relationship. What you're used to is the base 10, Beer's law, okay? And by the way, both of these are Beer's law. It's just a matter of which constants you're using, okay? So what you're more familiar with, this eta term, or E, that's the molar absorptivity, right? Which in fact is really the same thing as the absorption cross-section. It's really the same thing. However, the units are different, right? We know that molar absorptivity is liters per mole per centimeter, all right? This is concentration in mole per liter, and then this path length, right, is still the same. That's still centimeters. So that still cancels out all of our units, right, if concentration is expressed in mole per liter. However, when comparing eta to sigma, okay, so they are directly comparable. However, we have to consider there's a difference in units, right? One is liter per mole per centimeter. The other is centimeter squared per molecule. So that's just a conversion that can be accomplished with the liters to centimeters conversion, as well as moles to molecules. That's all you have to do is convert mole to molecule and liter to centimeter, and these will work out. However, additionally, you have this factor of 2.303 that you also have to use if you're converting molar absorptivity to a cross-section, right? So we recognize that this A, if I expand on this, that's 2.303 times eta times C times L, all equals sigma times N times L. Sorry, that got a little crazy. So you can see if you want to convert molar absorptivity into cross-section, you have to multiply the molar absorptivity by 2.303, as well as the mole to molecule conversion, as well as the liter to centimeter conversion, okay? So keep that in mind. And I'm gonna start showing you when we see various spectra or photochemical properties of molecules, you will actually sometimes see down in the notes whether something is a base E measurement or a base 10 measurement. And when you think base E, you should think that's cross-section. That's the fundamental unit. When you see base 10, that's molar absorptivity, which is the log 10, the base 10 measurement. Okay, moving forward. So here's some spectra of some various halogens. We've been talking a lot about the halogens, so I thought this was a pretty cool spectra to show you. The first thing I'll show you right away here is look at the Y scale, okay? So you're used to seeing an absorption spectrum as A versus lambda, right? Absorbance, where you get, some kind of peak, right? Owing to where the molecule absorbs that radiation. However, if you express a spectrum in terms of its cross-section, right? There it is, centimeter squared per molecule. And look, it's telling us base E, fantastic. Then you have an absorption spectra where you don't have to specify the concentration, nor do you have to specify the path length. It is a general fundamental way of looking at a spectra. Concentration, path length, not required. The other thing that I want to show you is oftentimes, so if we write 10, 20 sigma like that, like it is done here on the scale, that means the cross-section has been scaled up by a factor of 10 to the 20, okay? So in fact, what that means is this number right here, this 3.1, that's really 3.1 times 10 to the minus 20 centimeters squared per molecule. So cross sections are supposed to be very small numbers, which makes sense because if you think about this as a cross section, right, like as some cross sectional area, right, where light passes through. So if let's say I've got a bunch of waves passing through, this is really what this cross section is giving us, okay? So then perhaps these beams of light were being absorbed by that cross section. So now only those beams right there will make it through, okay? So it does represent like some cross-sectional area that's a target for photons. So it's supposed to be a small number. So just keep that in mind. When you see the exponent in front, 1020 sigma, what it really means is sigma times 10 to the minus 20. I know that's a little backwards, but that's common in the literature, okay? So now what I want to point out, I'm going to highlight a few things. Let's start with purple. So this number 1 here, oops, I wanted purple because as you can see, it's in the ultraviolet region. So I'll highlight this spectra right here. Here we go. Spectra number 1 right there is F2, all right? And you can see it's got a lambda max, you know, something like around 275 nanometers or so. All right. So if I was doing photochemistry with fluorine, I would want to select a light source that's somewhere between these wavelengths for fluorine, right? We can see fluorine absorbs between 200 and all the way to 400. So if I picked a light source to do photochemistry on fluorine way out at like 600 nanometers, nothing's going to happen. The fluorine doesn't absorb 600 nanometer light. What I would really want to do is choose a light source that's very close to the lambda max, right? That would give me the fastest possible photolysis rate constant, okay? So the next one, let's see, I'll go with maybe like a blue color. Okay, so the next one, as you might guess, in order of the periodic table is going to be chlorine. Right there it is, number 2, chlorine gas. Okay, very cool. And you can see its lambda max shifts to a slightly longer wavelength, which makes good sense when you consider the ionization energy and the other periodic trends of these halogens. All right. And then now let's see here. You can see number 3, hopefully you might guess, is going to be bromine. Let's pick a nice orange color for bromine. All right, so bromine's got that interesting little shoulder right there. So lambda max for bromine is around 400 nanometers or so. And then finally, let's use red. Iodine, Igor. Okay, so scales as well. And what's kind of cool about this, if you read through this, right, so fluorine is a gas at 25C. Chlorine is a gas at also 25C, but for some reason the spectra is at 18C. Bromine is a gas at 25C. However, iodine is not a gas at 25C. So that's why this iodine, you know, number 4 and 5, there's some subtle differences. Number 5, the one I highlighted, is actually iodine gas plus 1 atm of bath gas, of atmosphere. Whereas this number 4 is just pure iodine. And so there's some interesting things going on there. We'll get into those details when we get into spectroscopy. So, but I mostly wanted you to be aware of this trend for the series of halogens, but also just as an example of if I was doing photochemistry on the halogens, I really want to select a light source that's appropriate for a given halogen, okay? Or whatever molecule I'm interested in, all right? So moving along, so let's talk about some definitions, okay? So there are primary processes from photochemistry. So that's where products are formed directly from the excited state of a reactant, okay? So we consider the very first step in any photochemical reaction is A plus H nu. So, right, remember that's symbol for photon, H nu, okay, goes to a star, so excited state, okay? So in any photochemical process, this is the first step. The molecule has to absorb a photon. And it happens really, really insanely fast. 10 to the minus 16 seconds. So that's roughly 100 atto seconds, okay? Atto. 1 attosecond is 10 to the minus 18. And did you know that actually the fastest man-made event in human history is a laser that can be fired at pulses roughly every 70 attoseconds. Someone at Berkeley was able to do that. Of course, it was Berkeley. And it's the fastest human event ever done. A laser that can fire every 7 times 10 to the minus 16 seconds. Crazy fast. So this is not going to be the rate limiting step. It's super duper fast, okay? So primary processes are products formed directly from the excited state of a reactant. So that would be now this excited state goes on to form products, okay? So secondary processes are products that are formed from intermediates that are formed directly from the excited state of a reactant. So for example, in secondary photochemistry, A star might form some intermediate, and then that intermediate goes on to form a stable product, okay? And so we classify these processes, or I should say we quantify them by the quantum yield phi. So this definition is number of excited molecules proceeding by process I divided by the total number of photons absorbed, okay? So there's a couple different ways we could think about that. So for example, if I have, suppose A absorbs 100 photons, or rather I should say, suppose I irradiate A with 100 photons, okay? And perhaps maybe only one of those photons leads into doing photochemistry. So in other words, one out of those 100 photons went on to make an excited state, which then went on to make products. That would be a quantum yield of 1%, right? 1 out of 100 photons, okay? So then suppose, so what happens to the other photons? Well, suppose some of them lead into the molecule undergoing fluorescence or phosphorescence or intersystems crossings, or all of those lovely things you learn about in a Jablonski diagram. I think mostly you learned that in Chem 441. I know some of you haven't taken that class yet. We will do Jablonski diagrams ad nauseum in Chem 362. So you're going to see Jablonski diagrams again. So another way we could think of phi in terms of kinetics, there's another definition, and that would be the rate of a specific process, okay, divided by the intensity of light absorbed, okay? So often these things are pretty difficult to calculate. We usually rely on people determining quantum yields for us. Okay. So I'm going to show you a couple more things that can happen with quantum yield. Okay. So mechanisms of decay of excited states. All right. So the first thing we can say is, so I'll use the letter S to describe a singlet state. Okay. So we talked about this briefly, but just to remind you, a singlet state is an electron pair. Singlet. A triplet state is an unpaired set of electrons. And actually, I think in the last lecture, I forgot to describe the doublet state. And the doublet state is just one single unpaired electron. And it's called a doublet because it could be spin up or it could be spin down. Okay? So I don't have a periodic table in front of me, but A sodium metal, for example, is a good sodium metal, right? It's got a 2s1 electron configuration. That's a doublet, okay? So let's just talk about an arbitrary singlet state, a molecule possessing a pair of electrons, okay? If we irradiate it with H nu, and I'm going to say H nu initial, it could go into some excited state, and we call that absorbance. That's crazy fast. We often don't even consider the rate of that step, okay? And now we see the decay, so another possibility, okay, is this excited state could decay just back down to the ground state and emit light as a result at some different frequency, and we call that fluorescence, okay? And I'll say that happens with rate constant Kf. And here, this is fluorescence because the product H nu I is greater in energy than the product H nu F. So it's fluorescence, right? You have to use a more energetic photon for the absorbance, like a UV photon, for example, and it will give off a visible photon, like a blue photon, okay? So that's called fluorescence. So another thing that could happen, of course, is our excited state could just decay back down to a ground state. We call that internal conversion, and that happens at, I'll say that's rate constant K IC, okay? Or our singlet excited state could actually convert into a triplet excited state, and that's called intersystems crossing. I'll call that ISC, intersystems crossing. And as it turns out, that is very slow. It's very slow because it's very unlikely that a singlet state, right, a pair of electrons will just decide it's going to flip. All the same, it can still happen, okay? And so now if we think of the lifetime of an excited singlet state, and by the way, all of these are first order. All of these are first order exponential decays. So all of their rate constants are 1/seconds, okay? So the lifetime of an excited state we can give by tau, okay? And that's just going to be 1/k, right? Because these are first order reactions, so the lifetime is just 1/k. However, if we think of the total lifetime of our excited state, it's really going to be 1/k fluorescence plus 1/k intersystems crossing plus 1/k internal conversion, intersystems crossing, okay? You know, another one that I didn't define either, we'll put it on right here. My singlet state could decay into a triplet state, and then that triplet state, sorry, let me describe this as a ground state triplet state, and as a result, it would have to give off light, just like in this case. We call that phosphorescence, okay? I'll say that's K pH. That's also very slow, but all the same, it's a possibility, so we could put that on there, okay? So if we think about our total lifetime, so if we think about now going down the pipeline, right? I blast some light at a molecule. It absorbs that light. These are all of the things that it could go through, right? All of those energies could go funneling down the pipeline until we're just back to our normal ground state. And the lifetime of that process would be 1/all of those rate constants, okay? But for example, suppose we wanted to know the quantum yield of perhaps fluorescence, just as an example, okay? So then my quantum yield of fluorescence would be K fluorescence divided by K fluorescence plus K internal conversion plus K intersystems crossing plus K phosphorescence. So we could talk about the quantum yield of any one of these processes by looking at its individual rate constant divided by the total rate constants. All right? Okay, so, and you notice that this doesn't have anything to do within the chemistry that can then go on from that excited state, right? It's just how long does that excited state live? And as it turns out, right, we didn't even talk about the absorbance. It's so fast it doesn't even play a role in there, okay? So as it turns out, the fluorescence channels and the interconversion channels, internal conversion, excuse me, those will go very fast and those will dominate the decay of an excited state. So intersystems crossing and phosphorescence might not even occur because the fluorescence or the internal conversion might just take all of your excited states back down to the ground state. Okay. So moving along, now we finally arrive at what we call the photolysis rate constant. And what that photolysis rate constant gives us is the rate constant for chemistry, for a chemical process. So in other words, A absorbs some photons and goes on to make whatever the stable products are, okay? So we know A is going to absorb a photon and make an excited state, and there's all kinds of possibilities that that excited state can do, including going on to form a product, okay? And for that specific process, we call that Kp for photolysis rate constant. And as it turns out, this is more often than not the rate determining step, okay? So all of these other decay mechanisms for excited states are very fast. They're incredibly fast compared to chemistry, all right? So that's why we often only really think about the photolysis rate constant, Kp. We don't worry about the fluorescence rate constant or the internal conversion rate constant or the absorption rate constant because, again, they're very fast. So here's how we calculate a photolysis rate constant, okay? So it has to be calculated. You can't just have a general photolysis rate constant because it's dependent on the available light, okay? So dependent on available light. So there's two versions of this equation, so I'll describe them both. So this first one assumes that you have a broad continuous spectrum, okay? So for example, suppose, so I'm going to say, I'll call this I0 versus lambda. And maybe it looks something like this. And by I0, what I mean is that is my incident radiation to my sample, okay? So this spectrum that I just kind of drew up here, that would be the spectrum of my light source. Not the spectrum of my molecules, it's the spectrum of my light source. Like what color light am I using? How much intensity there is? And so now you can calculate a photolysis rate constant of that by integrating the quantum yield of absorption of the molecule, right? So, or excuse me, quantum yield for photochemistry. So that's what that gives you. So for the photochemistry, so in other words, phi of photochemistry, let's write it over here, phi of lambda of photochemistry is going to be Kp divided by Kf divided by Kisc divided by Kic divided by Kpf, okay? And to a reasonable assumption, most photolysis rate constants can assume to be 1. So in other words, when you add up all of these rates, they're all approaching that of the rate of photolysis itself because you're adding up all of those individual processes. Another way to think of it, instead of thinking of it in terms of the rates, Really a better way to think of it is, if I blast this molecule with 100 photons, all of those contribute to photochemistry. That's more of a reasonable approximation. So now this sigma, you know this, that's the cross section, okay? Right, and that's in square centimeter per molecule. Quantum yield is unitless. F, this is called the flux. And that's going to have units of photons per square centimeter per second. So you can think of it as the density of light used. So it's very much related to the intensity of light. However, it's flux, given that it's photons per square centimeter per second. And then, of course, d lambda, so we would integrate across a broad source of light. Okay. So you can also use this version of the equation. So instead of integrating, you can just do a sum of the products of all three of those things, right? So if you know the quantum yield at a given wavelength, if you know the cross section at a given wavelength, and you know the flux at a given wavelength, then you just multiply all three of those together, okay? And if you have a monochromatic source of light, so suppose you only have like one single wavelength coming through, then you don't have to carry out that sum, okay? You just multiply them all together and you go for it. So let's do an example of that. So here I've got some data. I know this is kind of hard to see, but here this is wavelength, and then these are absorption cross sections. Look at that, base E. For Cl2, Br2, and this rather interesting BrCl, I wanted to find a table that had at least some halogens on it. So the BrCl is kind of a weird one. So let's play with bromine for a minute, okay, and calculate the bromine photolysis rate constant. So we notice here, basically, if I were to plot all of these values, if I were to plot sigma versus wavelength, then I would get this. I'd get the absorption spectrum, which is kind of cool. So if I scan through those numbers here, you can see that they increase, that they increase, that they increase. Aha, here's a maximum, and then they start to decrease, okay? So that is giving me an absorption spectrum. And we notice here it has a maximum at, 420 for bromine, okay? So if I was deciding on a, photochemical reaction that I wanted to do involving bromine, I would want a 420 nanometer lamp. And if I had the ability of using a monochronometer, then I would select only that 420 nanometer lamp, and I would calculate my photolysis rate constant based off of that. Well, what if I didn't have a monochronometer, right? What if I had a broad source of light? Well, then I could still use this version of this equation, this sum, okay? And all I'd have to do is calculate a photolysis rate constant at each wavelength, right, at each value, and then add them all up. So here's how this goes. So for now, and this is perfectly okay in your Kinetica simulations. For now, we'll just assume that phi equals 1. That's a fairly reasonable assumption. We're going to say sigma, here it is, it's 64.8. And then look, the 1020 is in front, so that means it's 64.8 times 10 to the minus 20 square centimeter per second, or per molecule, sorry. Okay, now how do I calculate the flux? Well, as it turns out, flux, okay, is pretty straightforward to calculate. It's power divided by energy times area. That's it. Power divided by energy times area. Okay, so the power, we have to make a few assumptions about the power of our light source. In other words, is it 1 watt or 2 watts or 20.532 watts, 8.62 gigawatts, right? We don't know. I have to look at the light bulb and tell you what the power of that light source is, okay? So depends on the light source. Okay. What about the area? The illuminated area of the light source. Well, also, that depends on the light source. Okay. And typically in a photochemistry reaction, so let's say here I'm going to draw like my lamp, my light source, right? I'm going to draw my like classic looking light bulb here. Okay. Definitely not an LED, right? That's my classic incandescent light bulb. Okay. And so suppose now I had a beaker that I was like doing my photochemical reaction in. Let's say right here's my beaker. I wouldn't just blast this whole beaker. Well, really, I shouldn't even say it's a beaker, right? We're doing gas phase chemistry. So maybe it's a flow cell. Okay. So let's just say here's like my flow cell. Okay. So if I was shining all of this light around, it would be really difficult to know what my illuminated area is. So that's why we often use a very technical device called a slit. Simple as that. So it might be like a piece of metal that has a hole in it, okay, with known geometry. And so what that means is now my illuminated area is going to be really well known, right? And so I can use this light source that's blasting light everywhere. But if I want to do a nice controlled photochemical experiment, then I'm going to use a nice controlled like little area like to shoot the light through. So we have to make some assumptions about that as well. Okay. So the only thing we can really calculate is the energy. And this is a nice stroll back into the good old days of Gen Chem, right? E equals hc over lambda. So suppose we were going to use this 420 nanometer photon. Okay, so I'm going to make a couple assumptions here. Okay. Suppose we use a 420 nanometer lamp, and we'll also suppose that it's 1 watt, and we'll also suppose that there's a 1 square centimeter opening. So if we're calculating a rate constant, right, if we're not doing the experiment, we're kind of free to make these assumptions. So then how do we do it? Well, I would literally say flux equals, it's going to be 1 joule per second, because that's 1 watt, divided by, and then I would do, H times C divided by 4.20 times 10 to the minus 7 meters. Okay, so I don't have my calculator up there, but I'm going to do that really quick. 6.626 E minus 34 times 2.998 e to the 8 divided by 4.2 e to the minus 7. Okay. So for that, I got 4.73 times 10 to the negative 19. And the units of this equation are joule, and technically it's joule per 1 single photon. Okay? And then now, so it's flux is power divided by energy times area. So now I assume that it was a 1 square centimeter lamp, right? So we'll just say 1 square centimeter. And so now when I do this calculation, okay, let's see, that number. So basically all I have to do is flip that number because I've got 1 and 1, right? My flux becomes 2.11 times 10 to the 18. And let's see if these units work out, okay? The joule and the joule cancel. And now I've got 1 over photons, which is a photon per second per square centimeter. Okay? And oh my God, I ran out of room here for my calculation. So let's go to the next slide. So Kp equals phi times sigma times flux. So we assume the quantum yield is 1. That's a fair assumption. My sigma was 64.8 times 10 to the minus 20. That's the same as 6.48 times 10 to the minus 19 square centimeter per molecule, and my flux was 2.11 times 10 to the 18, and that's photon per square centimeter per second. And now if we look at the units here, square centimeter and square centimeter cancel. Photon and molecule cancel because with, right, this quantum yield, technically what the quantum yield would be, the unit would be one molecule is absorbed, or one photon is absorbed by one molecule. So we can cancel the photon and the molecule unit. And from this, I'm going to get 1 over seconds, which is a first order rate constant, as it should be. Okay? So we'll say that times 6.48 E minus 19. And so this Kp ends up being 1.37, 1 over seconds for a 420 nanometer lamp that is 1 watt, that is 1 square centimeter. Okay? So I know I'm talking a little bit long. I've just got a few more minutes to go. I just wanted to make sure that I show you how to calculate a photolysis rate constant. Because if you choose to do photochemistry in your Kinetica project, you're going to have to make some assumptions about calculating the rate constant. Okay? So let's do that. So I'm going to show you my model. So I've still got this hydrogen-bromine reaction, right? But now I added in a photochemistry model. Okay? And so here it is. So the mechanism is very similar. However, in that very first step here, there's my first step. There's no bromine plus M, right, to make the collision happen. It's just bromine absorbs a photon, and that photon directly leads to the production of bromine radicals. I think that I've got that. Yes, here we go, right? So in these linear chain reactions, this is kind of the last and final subject, right? We can initiate a chain reaction through heat, right? Oops, undo. So we can initiate it with heat, or we can initiate it with light. Both cases produce bromine radicals. Okay, pretty cool. And so now that's an initiation step. There, I've showed it to you, K1, okay? So in these linear chain reactions, anything that continues making more radicals, we call propagation. So you can see in the next step, whether it's initiated by heat or light, a bromine radical does a hydrogen atom abstraction on H2, right? So something like this. Okay, so it undergoes the fish hook mechanism, okay? And that makes a stable HBr, but it propagates the radical cycle because it's kicking out another hydrogen radical. Now, if there's an equilibrium of that, or in other words, if it takes that newly formed radical and pushes it back to stable product, we call that inhibition. Because ultimately that's going to limit the rate of this reaction, right? HBr is the final product we want to make. However, in this reaction, HBr is getting consumed backwards, right, to more reactants. So we call that inhibition because it's inhibiting this radical cycle. Okay, then we get another step, okay? So then now this H radical, so we produced another H radical that can then produce another bromine radical. So that's more propagation. And now finally, so this is why these two initiation steps aren't shown as an equilibrium, because now these two bromine radicals reforming via a third body reaction doesn't produce any more radicals. So it's a termination step, okay? And that's the only way these types of chain reactions stop, is not necessarily when you run out of reactant, rather when you run out of radicals. So we might have unreacted bromine or unreacted H2, depending on the conditions of this chain reaction. Okay, so now this is a 45-minute lecture. Oh my gosh, I'm sorry. I just want to talk a little bit about this now mechanism with light. And so I'll just compare this. So these were the results I did when the reaction was driven by heat. And I'll remind you of my conditions. 1200 Kelvin. I've got a third body in there at 1 atmosphere, okay? An inert third body. And my initial bromine and hydrogen are very low at 1017. So that's roughly 100 times less than the concentration of my bath gas, okay? So roughly like 0.01 atmospheres of bromine and 0.01 atmospheres of hydrogen and 1 atmosphere of inert third body. And at 1200 Kelvin, this reaction is crazy fast, right? It's over within 1 millisecond, okay? You can see bromine and hydrogen decay, and bromine is decaying at a different rate than hydrogen, and that's actually due to that 1/2 order interesting phenomenon of bromine. And I would definitely say bromine and hydrogen, even though it looks like they're produced at steady state, they are not, because this is a log scale, right? You can see there's a huge production of bromine radicals, right? It spikes up like 5 orders of magnitude, okay? And then later on in the reaction, it starts to hit a steady state. So let's compare that now to the reaction driven by light. And the only thing I changed in this mechanism is I dropped the Br2 plus M and just make it Br2 plus H nu. And then here my K1, right, is just phi times sigma times F. I assume my phi to be 1. There's my sigma, right, my cross section. And I said flux is power divided by energy, where energy is Hc over lambda. Okay, so I solve all those problems. Here, I'm making the temperature equal to 350 Kelvin, and I'm using a 100-watt lamp at 1 square centimeter. And these are the results. Completely different than the reaction initiated by heat. For one, look, it takes 100,000 seconds for this reaction to proceed versus the 1 millisecond, right? So 100,000 seconds is several hours, all right? The other thing you notice is bromine and hydrogen are absolutely produced at steady state throughout the entire reaction. Look at this. Almost instantaneously, bromine radicals are generated at a really large concentration, which is really cool. So that photolysis step is really fast. It's generating bromine radicals immediately, but what it's doing is it's generating bromine radicals at a steady state. You also notice that it's producing hydrogen at a fairly steady state. However, the concentration of hydrogen is way smaller than the concentration of hydrogen generated up here, right? Hydrogen spikes about 10, 13 molecules per cubic centimeter, and the reaction driven by light, hydrogen barely hits 10 to the 7 molecules per cubic centimeter. So huge differences. And I'm also going to change this log scale just so you can see it in a little bit more detail here. Let's hope that works. Yes. So you can also see you can't even distinguish bromine and hydrogen because I set them both to be the same concentration. If let's say I make bromine like just a little bit different, you'll be able to see now super dynamic, right? They're not necessarily the same. You can see HBr is produced really quickly right away, but then tapers off and starts undergoing a steady state production. Okay, so these reaction profiles are just completely different whether driven by heat or light. And we could really dive into like all these steps, what's going on there. But that's what I want you to do in your project. I want you to think about all these steps that are going on, kind of like how I described them, by noting, look, steady state production of bromine. So there's always a steady production of bromine radicals. How is that going to influence the reaction down the line? Okay, so this stuff gets really, really interesting. I could also play with this and I could turn down the power of my lamp. and see how that changes the reaction. I could, I had to make this go at about 350 Kelvin to see something reasonable. I could certainly turn this down to room temperature and see how that plays out, okay? So all interesting stuff that I want you to kind of self-discover in your Kinetica project, all right? Sorry that I went a little long on this one. I will see you on Friday.